Hello everyone, I'm Frank and welcome to Frank Puzzles, and this is today's easy level puzzle. And take that easiness with a grain of salt, because it's considered easy by the people on the Logic Masters Germany forum, and there's a lot of really smart people there. Today's puzzle is called Roman Negativity by Yitrio, and here are the rules. We have normal Sudoku rules apply, which means in every cell in the grid, place a single digit such that every row, column, and designated 9-cell region contains the digits 1 through 9 exactly once each. We have yin-yang shading, where we need to shade some cells such that all shaded cells are orthogonally connected and all unshaded cells are orthogonally connected, and no 2x2 area is fully shaded or fully unshaded. So this is an example of a valid yin-yang shading, because what does it mean to be orthogonally connected? As a region, it means that you have to be able to go from any cell in the region to any other cell in the region just by going through edges, all while staying within the region. So for example, you can go from this cell to this cell here by going through these edges while staying within the shaded region. To get from here, this cell here to this cell here, you can go from these edges, all while staying within the unshaded region. So that's an example of this is an example of a valid yin-yang shading. Now, what are examples of invalid yin-yang shadings? You could not have something like, say, this, because these cells no longer connect to the cells here or here by just going through edges while staying within the region. It would have to go through a corner, or it would have to go through an edge and exit the region, neither of which is allowed for orthogonally connected regions. This also would not be a valid yin-yang shading, because we have a 2x2 area here that's all fully shaded, and we cannot have a 2x2 area that's all fully shaded or fully unshaded. So those are examples of how yin-yang work. Values separated by an x sum to 10, and values separated by a v sum to 5. Not all possible x's and v's are necessarily given. So as an example, say this was 3 here. Oops, not dark. Say this was 3 here, then this would have to be 2, because these two digits must add up to 5, because there's a v between them. Or say this was a 3, this would then have to be 7, because these two digits must add up to 10, because there's an x between them. Okay. Oh. Values separate. Okay, so. Right, value separated by an x sum to 10. Value separated by a v sum to 5. And not all possible x's and v's are necessarily given. This is actually not going to work, because, anyways, we'll talk about that later. We have orthogonally adjacent values cannot have a difference of 1. So for example, if these were both valid, it would have to be, and this could not be 2 and 3, because they would have a difference of 1, and orthogonally adjacent values cannot have a difference of 1. And these are orthogonally adjacent values means just that they share an edge. So keep that in mind. And the key thing here, which I totally didn't understand, is digits in shaded cells count as the negative for their value, the negative of their value for the purposes of the xv and the difference constraint. So this actually could not add up to 10, because this would be negative 3 plus 7, which adds up to only 4. So obviously that's not going to work. So all shaded cells, basically, the value of that cell is the negative of the digit. Okay. Anyways, those are all the rules. If you'd like to play along, there's going to be a link in the description. And now, I'm going to get started. Let's go. Okay. That means any two digits adding up to 10 cannot be shaded. So these are all unshaded. These are all unshaded. This is a 2, and these, all the 10s have to be unshaded. We have a 2x2 area that's all unshaded, so this must be shaded. And this cannot be 4 unshaded cells here, because that would be, this unshaded cell could not orthogonally connect to, sorry, the shaded cell could not orthogonally connect to the rest of the shaded cells in that case. So you cannot have a 4x4 all shaded cells here. Hmm. Okay. For any V, you're going to have at least one of the digits be unshaded. Because if you have 2 shaded cells in the V's, that's not going to work because they add up to a negative sum. And they will not obviously add up to 5. So one of these has to be green. One of these has to be green. If this were this cannot be blue. If this were blue, that would force this to be green, and then the blues are not orthogonally connected. So this must be green here. One of these is green. We don't know which one though. Okay. Either way, 5 can never be next to an X and can never be next to a V. To add up to 5, because 5 plus 5 adds up to 10. 5 plus 0 adds up to 5. And if you have a negative 5 there, negative 5 plus 15 adds up to 10. Negative 5 plus 10 adds up to 0. So none of these can be 5, which means 5 has to be here. That means the remaining digits here. So these remaining digits have to be either, to add up to 10, well, one of them is going to have to be negative. So you're going to have a digit 5 less than it subtracting out. So it's either 6, 1, 7, 2, 8, 3, or 9, 4. To have the others add up to 10, so the 10s are either 1, 9, 2, 8, 3, 7, and 4, 6. 6 and 1 means that you cannot have 1 and 9 or 4 and 6 adding up to 10. So you're guaranteed this has to be 2 blues here. Right? Because this cannot be... If you have you're going to have a difference here for the blue to get out orthogonally, to orthogonally connect to the rest of the blues. And because of that, you're going to have either 6, 1, 7, 2, 8, 3, or 9, 4, essentially subtract to 5. If you have 6, 1, or 9, 4 subtracting out, that means the 10 pairs that add up together must be 2, 8, and 3, 7. If you have 7, 2, or 8, 3 subtracting out, that means you have to have 1, 9, and 4, 6 as the digits that sum to 10 in this box. So if you have 6 and 1, that means the other remaining digits in that will add to 5 is 9 and 4. Well, they obviously can't add to 5, so one of them must be shaded. So you always have, and it's the same thing with 7-2 with versus 8-3. So you always have two shaded, so you'll have two shaded cells to add to 5, and obviously this must be blue. And then we have a blue-green pair here. This must be the smaller of the digits, so this is 1 through 4. So we have swapped digits here. That's interesting. Orthogonally adjacent values cannot have a difference of 1. So this is -5. So this cannot be -4 here, which means this is correspondingly 6, 7, or 8 here. Hmm. Hmm. We don't know which one of these is blue. We have to have a green here. Oh, one of these has to be green. So in yin-yang shading, you can only swap on the edge of the grid, the shading, 0 times or 2 times. Because if you try to have more than that, if you try to have 4, first of all, you can't do 1 or any odd digits of switching. Because if you swap here once, it's going to have to swap back eventually to get to this color. And with the amount of swappings you can have, it only must be even sets. So this has to be green here. We have to have a green here in the V's. So we know that to connect to greens here, guaranteed, these all have to be green because you cannot swap more than twice on the edge of the grid. Therefore, these are all green. This must be blue here because of the 2x2 area. That's all green. Same with that. Same with this. Okay, the reasoning. Let's do the reasoning first. The reasoning is if we tried to swap here to make this green and then we swap back to blue here, and then before we swap back to green, how do you orthogonally connect the blue regions together without breaking the green regions into two regions? You can't. Same with orthogonally connecting the green regions. How do you do so without breaking the blue region into multiple regions? And the answer is you can't. So that's why these are all green here, because you can only swap 0 or 2 times on the edge of the grid, and we're guaranteed this has to swap. So again, this is blue, this is blue. Every V has to have a green with it, so this is green. The blue has to orthogonally connect, so that's blue. This is not necessarily green. We know that this has to be green, though. So these must be 1 through 4. These are orthogonally orthogonally adjacent, so it cannot be 2, 3. It must be 1, 4. Actually, all the V's that are orthogonally adjacent and that are both positive values must be 1, 4. So this cannot be 2, 3 because of that would force those digits to be orthogonally adjacent and have a difference of 1. So this must be blue here. This cannot be 2, 3, so this must be blue here, which means this has to be blue all around here. This is a 2x2 area that has 3 blues, so the last digit must be green. This is blue, so that forces this to be green here. These cannot be 2 and 3 as the lowest digit, and they have to be 2 and 3 if they are the smallest digit. Because if these were -2 and -3, that's a difference of 1 between those values. So this cannot be -2 and -3. It must be -1 and 6. This must be -4 and 9. And this has to be a 2, 3, 7, 8 triplet. 8 can't be here, so 2 can't be here. 7 can't be here, so 3 can't be there. This must be green to add up to a positive value. Cannot be 4. Cannot be 1, 4. This has to be then 2, because it can't be -3. -3 is has a difference of 1 with -4. So this is -2, which makes that a 7. This is 3 green cells, so this can't be green. That's blue. We have a diagonal of a blue here. So that there are two deductions you can make for yin-yang shading. One was that on the edge of the grid, you can only swap colors 0 or 2 times. If you have a diagonal which is the same shading, the other diagonal has to be one of that same shading and one of the other shading. And the reason why, so say we have a diagonal here that's all blue. Obviously, you can't have this diagonal be all blue, because then a 2x2 area would be all blue. But if we try to make this all green here, the problem is, how do you orthogonally connect the greens without breaking apart the blue into 2 separate regions? You can't. Same with the blues. How do you orthogonally connect the blues without breaking the green into 2 separate regions? The answer is you cannot. So, in this diagonal, we have a guaranteed blue here. So the diagonal must be 1 green and 1 blue. So therefore, this is the green, which makes this the blue here. This is green adding up to 10. You cannot have 7 or 9 here. So this is 2, 8, or 4, 6. It cannot be 2, 8 because of the 2 in the box. So this is a 4, 6 pair. 6 cannot be orthogonally connected to, or orthogonally adjacent to the 7, because that would be a difference of 1. So this is 4, that's 6 there. Okay. This adds up to 9. So this is the higher digit. It cannot be 9. It's 6, 7, or 8 with 1, 2, or 3. But this 1 can't be here because of the 1, 4 pair in the box. So this can't be 6. So we have -2 or 3 with 7 or 8. Okay. This must be 6 through 9, which leaves 1 through 4 there. Cannot be 1 or 4 because of the 1, 4 pair in the row. So this can't be 6 or 9. To subtract 2 of 5 here. 1 eliminates 1 here, so that's 4, which makes this a 1. This must be -2 or -3, which leaves us as 7 or 8 there. Remaining digits of column 1. We have 3, 5, 7, 8, 9. No 7 here. So 7 has to be one of these 3 digits here. So if this were an 8, that would have a value of -8, which would definitely be consecutive with a -7 in one of these remaining cells. So this cannot be -8 there. Remaining digits of column 2. We have 1, 2, 3, and 8. And we have a 1, 2, 3, 8 quadruplet now in box 7, which eliminates 1, 2, 3, and 8 in the rest of the box. So there's no 3 here, no 8 here. This is 5, 7, 9 as a triplet, which eliminates 5, 7, 9 in the rest of the column. So this has to be 3, 8 as a pair. This can't be -3 next to the 2, -2. So this is -8 next to the -3. Remaining digits, we have a 2, 3, 7, 8 quadruplet in column 4. And this actually cannot be 2, 3, 8, 4, 6, 7. So that leaves us as 1, 5, 9. So we have a 1, 5, 9 triplet in column 3 also. That leaves this as a 4, 6 pair here. And this being 2 or 3, one of these is 2 or 3, so this cannot be 2 or 3 here. So this is 7 or 8, which means this can't be 8 here. If this were 7 or 8 here, though, that would be definitely consecutive with the 7 or 8 that's guaranteed here. So this cannot be 7 or 8. It must be 3, which makes this 7. That makes this 8 and 2. 3 eliminates 3 here, so this is 2. So this must be 7 minus 2 here. 3 eliminates 3 here, so that's minus 2, which makes that 7 plus negative 2 is 5. We have 3 greens here. So this cannot be green, it's blue. It must orthogonally connect out, so that's blue there. We have the pattern here of a diagonal being the same color, so this cannot be the same color here, so this must be green. We have a 2 by 2 that's all blue. This cannot be blue, it's green. 2 by 2 that's all green, and here, so this must be blue and blue. Diagonal here of being blue, and it must orthogonally connect out, so that connects to there. This adds up to 10. No 7 in either of these. So this is either 9 and 1 there. 2 could be here with 8 there. No, 2 can't be here because of 2 in the box. So that's not allowed. No 3, 7. 4 and 6 is the possibility there. Remaining digits of row 2. We have 6, 8, and 9. Well, 8 and 9 are consecutive with each other, and they would all be negative. So this cannot be 6, 8, or 9. Sorry, this can't be 8 here, because this can't be 8 or 9 here, because that would force these to be an 8. It would force the negative 8 to be next to a negative 9 guaranteed. So this has to be negative 6 here, which means this can't be 6 here. No 6 here. Okay. This adds up to 10. Sorry, this is also green. We have a green diagonal here, so this cannot be blue here. It has to be green because that has to be different colors here. Blue has to orthogonally connect out, so that must go there. This is a 2 by 2 that's all green, so this is blue there. One of these at least is green. So if this is green, it has to go out this way. If this is green, it still has to go out this way. And the problem is, I guess both of them could be green also. So either way, you have to go out this way. And you cannot, so if we try to have a blue there, well, we can't have 2 greens. If this is 2 greens, it's a 2, 3 next to each other, which would be orthogonally adjacent values having a difference of 1. So one of these must be blue. If this is green and this is blue, we have to orthogonally connect out, and this is a 2 by 2 area that's all blue. So this cannot be green, which makes that blue and that green there. It must orthogonally connect out that way. This cannot be 6 or 9, so it's 7 or 8 next to 2 or 3 there. Okay, 2 eliminates 2 in the rest of the box, so this is 1, 3, 8. This can't be 1 because of 1, 4 pair in the row. This can't be negative 3 because that would be consecutive with negative 2. So this must be negative 8, which makes this not 8. This can't be negative 7 or 9 because it's consecutive with negative 8. So this is negative 5 here, which means these can't be 5. Remaining digits of row 9, we have 3, 6, and 9. 6 can't be here because of 6 in the column. To add up to 10 here, no 6, so it's 1, 2, 3, 7, 8, 9. No 3 here, so no 7 here. No 8 here, so no 2 there. Okay, this 7 eliminates 7 here, so this is 8 minus 3 is 5. 8 eliminates 8 here, so that's 9 and 8 there. 3 and 9 eliminate 3 and 9 here, so that's 6, which means this cannot be 6 here. Remaining digits in box 3, we have 2, 5, and 7. And this can't be 2, so this is 5, 7 as a pair, which forces this to be 2 here. 2 eliminates 2 and 8 to add up to 10 here. Remaining digits of row 1, we have 3, 4, and 9. 3 and 4 are consecutive with each other, so if they were here, they would be adjacent. They would share an edge with the other 3 or 4. So this cannot be 3 or 4. It's 9, which is next to 3 or 4 here and 3 or 4 here. Remaining digits of row 3 are 1, 5, and 6. Okay. Remaining digits of column. This is guaranteed to be... Okay, yeah. The remaining digits of column... Let's do column 9 first. We have 2, 3, 5, 6, 7, and 9. 6 cannot be either of these digits because of 6 in the box. 3 and 9 cannot be here because of 3 and 9 pair in the box. No 3 or 6 there. No 2 or 7 there because of digits in the row. Remaining digits of column 7. We have a guaranteed 3 or 9 here, and this must be 3 or 9. So actually, let's do remaining digits in the box. No 3, 6, or 9 here, so it's 1, 2, 4, 5, 7, 8. This can't be 2 because of 2 in the column. We also do not have 3 and 9 available, because again, one of these is 3 or 9, and this is 3 or 9. That eliminates 3 and 9 in the rest of the column. So this is also 1, 4, 5, 7, 8. Cannot be 7 because of the 7 in the row here. Okay. We are guaranteed one of these digits is going to be 1, and so therefore must have a negative 1 in value. If we had a 2 here, that would guarantee it's orthogonally adjacent to a negative 1, which is not allowed. So this cannot be 2 here. We have a guaranteed 1 or 4 in this pair adding up to 10 and this digit here. That eliminates 1 and 4 in the rest of the column, so this can't be 1 or 4. It's 3, which makes this 4. 3 eliminates 3 here, so that's negative 2, and therefore this is 7, which eliminates 2 and 7 here. So it's 5. This can't be 5 or 7. It's 2. That eliminates 2, 5, and 7 in the rest of the box. So this is 1, 4, 8. 7 eliminates 7 here. So this becomes a 1, 9 pair, which eliminates 1 and 9 in the rest of the column. So no 1 here, no 9 here. It's 3, which makes that 9. No 7 here, so it's 5 and 7. So there's no 5 here, no 1 here. It's 4, 8. No 2 or 5 or 9 here. So this has to be 7 here then. That leaves that as 7. This can't be 7. It's 3, 6 as a pair. 6 is consecutive with 7, so they cannot be adjacent to each other. So this is 3. That's 6. Remaining digits of column 8, we have 2, 4, 5, and 8. 4 and 8 cannot be here because of 4 and 8 in the row. No 2 here because of 2 in the row. Remaining digits of column 6. No 1, 2, 3, 4. So it could be 5, 6, or 7, or 9. No 7 here because of 7 in the box. No 6 or 7 here because of 6 or 7 in the row. I think that's fine. 7 eliminates 7 here. So this is 9, that's 7. Okay. -2 cannot be next to -1 because they're consecutive. So this is -5 or 6. We're guaranteed a 1 here. Remaining digits in this lower central box have to be 3, 5, whoops. 3, 5, 6, 8, and 9. No 5 here. No 9 here because of 5, and no 9 here because of 5 and 9 in the row, and 9 in the column there. Okay. 1 is guaranteed to be one of these two digits here. It's also guaranteed to be one of these two digits here. Where is 1 in column 4? It must be one of these 3 digits. This cannot be 6. It's orthogonally adjacent to a 7, and they are consecutive. So this is 1 or 5. If this were 5, this would be 9, which would force this to be 4, 6, and 5 and 4 are consecutive, so this cannot be 5. Where is the 7 in column 6? Well, yeah, I guess it can't be any of these, or these because of 7s in the rows, so this has to be 7 here. Interesting. That gives us all 9 7s. Okay. We have all the x's and v's solved, so it's now just the consecutiveness then. Okay. Four and 3 are consecutive, so this can't be 4, which makes this 1 that 4. 1 eliminates 1 here, so that's 6 and 4 here. That means this can't be 6. 6 eliminates 6 here, so that's 5, which makes that 1 there. So this is -5, that's 1, 6. This can't be 5. Where is 5 in box 8? Cannot be here or here, so it must be here. If this were green, these would be, there would be difference of 1, and they would share an edge, which is not allowed. So this must be blue. We have a 2 by 2 that's all blue, so this can't be blue here. It's green. 5 wait. 5 could be here also. Oops. One of these is 5. Okay. Never mind. That wasn't good. We have a 1, 5, 9 triplet in row 6, which eliminates 1, 5, and 9 in the rest of the row. So that leaves just 2, 4, and 8 remaining. Also, 4 eliminates 4 here, so that's 8. This can't be 4, 8, it's 5, which means that can't be 5, it's 2. That leaves this as a 4. So this is a 2, 8 pair here. This can't be 2 because of 2 in the column, so this is 8, that's 2. That eliminates 8 there, so one of these two has to be 8. 5 eliminates 5 here. And the remaining digits in row 4 are 1, 3, and 9. No 1 or 9 here because of 1 or 9 in the column, so that's 3. No 3 here. This is a 1, 9 pair here. 3 eliminates 3 in the rest of the column. Remaining digits of column 5 are 5, 6, and 8. Obviously, this can't be 8 because of 8 in the row. Remaining digits in this cell specifically are 1, 5, 6, and 9. Interesting. We have 2 here. 4 can't be either of these digits. It's a 1-8 pair. This 8 eliminates 8 here, so that's 4. This cannot be -5. That's 1 away from -4. So this must be 9 here, which leaves that as a 5. So again, we have to have 5 here. 9 eliminates 9 here, so it's 5, which makes this 6. No 5 or 6 here. 5 eliminates 5 here. Where is the 5 in box 4? It must be here. And like these two situations, if they were both green, they would be 1 away and share an edge with a 4, which is not allowed. So these both must be blue. That forces both of these to be green because they have 3 digits that are blue in the 2x2 area. -5, 9 can't be 9 here. This must be 8. Which makes this 1, which makes that 8. 1 eliminates 1 here, so it's 3 and 1 there. 3 eliminates 3 here, so it's 6 and 3 there. 4 eliminates 4 here, so it's 6 and 4. 7 cannot be, would be consecutive with 6, so this must be -6, so this is blue. Green has to orthogonally connect out. We have a diagonal here of blue, so this cannot be green, green, so this must be blue here. We have a diagonal of green here, which means this can't be blue, blue, so this is green there. Hmm. 6, 3. Hmm. 8 and 9 would be consecutive, so this must be 1, which makes this 9, which makes that 1. So this is 9 here. That would leave that as 1 and 9 there. This 9 would be consecutive with 8 if it's green, so this must be blue. 6 and 8 there. We have to orthogonally connect here. These cannot be the same shading, so we know there's a boundary here. Because there's a 3 and a 4. If they were the same shading, they would have a difference of 1, guaranteed. If this were blue, it would have to orthogonally connect out here, and then this would not be not orthogonally connected to the rest of the greens. So this cannot be blue, which makes that green. So then this must be blue to make sure that they don't have a difference of 1. We have to orthogonally connect the blue regions, so this is blue. We have to connect the green regions orthogonally, so that's green. And that leaves this as a 9 and this as a 1. And that's a solution. So obviously, okay, let's double check. 2 and 8 add up to 10. 3 and 7 add up to 10. 6 and 4, 1, 9, all add up to 10. 6 minus 1 adds up to 5. 1 plus 4 adds up to 5. 7 minus 2 adds up to 5. 9 and 4, 7, 2 add up and subtract to 5. 8 and 3 subtract to 5. 7 and 2 subtract to 5. 1 and 4 add to 5. 7 minus 2 subtracts to 5. And the green digits cannot have consecutive digits next to them. 1, 3, 6, 4, 7, 9, 7, 3, 8, 2, 6. 8, 4, 9, 7, 1, 6, 2, 4 with the 6. 4, 7, 9, 1, 7. 1, 8, 6, 8. 6, 3, 3, 7, 7, 4, 4, 1, 1, 3, 3, 6, 6, 9, 9, 2. 5, 7, 3, 6, 8, 4, 1, 7, 5, 3, 9. And check the negative digits, same thing. 5, 1, 4, 2, 8, 3, 9, 7, 5, 8, 2, 6, 4, 9, 5, 1, 9. Going this way, 5, 2. Going this way, 3, 6, 2, 5, 2, 9, 5. 9, 4, 8, 1, 4258 5339 968. So none of those are consecutive. I hope you enjoyed this solve, and I'll see you next time on Frank Puzzles. Take care.